Imagine the scenario. You're running a critical production line. Maybe it's for, I don't know, precision medical devices or huge power plant components. And suddenly, bang, a crucial piece of machinery shows a dangerous defect.
Or maybe even worse, a component that's already out there, in the field, actually in use, it just cracks under pressure.
Exactly. Production just grinds to a halt. Safety, obviously, becomes the #1 concern. And the immediate urgent need is, well, it's a fix. But what kind of fix? And how involved does it get? How do you get things back on track?
Yeah, it's a big question.
So today we're taking a deep dive into the often overlooked yet absolutely critical world of weld repairs. Now, that might sound like, a simple patch-up job, but trust us, it's really anything
Like,
but.
definitely not.
Our mission today is to sort of unravel the complex decisions and the, well, incredibly detailed processes behind fixing things with welds. We want to reveal why just saying fix it is rarely simple and how it impacts everything from structural integrity right down to the bottom line.
And we should mention, our insights are coming from some really detailed technical documentation on weld repairs. It gives a pretty fascinating glimpse behind the curtain, actually.
It really does.
It's interesting. We usually think of welding as something you do when building something new, right?
Yeah, absolutely.
But the reality is an immense amount of welding expertise goes into fixing things that are already broken or have defects. And like you said, it's definitely not a one-size-fits-all kind of approach.
That's a crucial distinction, isn't it? So let's imagine we're on the shop floor at, let's call it Apex Turbines, right? A company making massive turbine blades. When we talk about weld repairs there, they're really two distinct arenas.
Right.
On one side, you've got production repairs. These happen during the manufacturing process itself. So think of it like finding a slight imperfection in a brand new turbine blade before it even leaves the factory.
Exactly. And then the other side is in-service repairs. Now, these are the ones that happen to components already out in the field, doing their job like that turbine blade that's been spinning for years in a power plant.
Okay.
What's absolutely vital to understand here is that unlike, say, planned maintenance or refurbishment, these repairs are almost always unplanned.
Right, they're surprises, usually bad ones.
Exactly. And they often come with intense production pressures. I mean, really intense. If you don't have a crystal clear policy already in place, that pressure can, well, unfortunately, it can lead to dangerous shortcuts.
Oh, I can absolutely see that. Time is money, right? And when something breaks unexpectedly, the pressure to get it back online must be immense.
It is.
So for these local or on-site repairs, especially the ones out in the field, are there sort of preferred methods, things that lend themselves to quick but still reliable fixes?
Definitely. Manually controlled welding processes like MMA, that's manual metal arc, are often the easiest to use in those situations.
Okay.
Why is that?
Well, they're incredibly versatile, they're highly portable, and you can find a wide range of consumables pretty much off the shelf. That makes them a real go-to for on-site fixes.
Right.
However, there's a crucial general rule you absolutely have to remember. Repairs almost always result in higher residual stresses and increased distortion compared to the first-time welds.
Hold on. Residual stresses and distortion. Okay, for those of us who aren't welders, what does that actually mean for the component, like practically speaking?
That's a great question. Think of residual stresses like invisible internal pressures.
Yeah.
Or tiny microscopic springs kind of compressed inside the metal itself.
Okay.
They can make the repaired area more brittle or maybe more prone to new cracks developing down the line. And distortion, that's simply the part bending or twisting out of its intended shape.
Which could mess up how it fits or performs.
Exactly. It can throw off its fit, affect its balance, lead to further structural issues. That's why for certain steels, like carbon manganese and low to medium alloy steels, pre- and post-weld heat treatments might become absolutely necessary.
To manage those effects.
To manage those effects, yeah, and prevent long-term problems. It's all about mitigating risk.
So it's never just a quick patch and go situation. It sounds like every single step here is critical. But even before the sparks start flying, what's the very first, most fundamental hurdle you have to clear before you even think about doing a weld repair?
Well, if we connect this to the bigger picture, the absolute most important factor before you undertake any repair is asking, is it financially worthwhile?
The bottom line.
It sounds purely economic, right?
Yep.
But it really underpins everything else, because answering that question forces you to answer a whole load of other critical questions. You could say the ultimate takeaway is that weld repair isn't just about applying heat. It's this Rigorous, multifaceted risk assessment and economic feasibility study before a single spark flies.
Okay, that really puts the pressure involved into perspective. So let's unpack this a bit more. What are those crucial questions a fabricator or whoever's responsible has to ask?
Okay, well, first off, can structural integrity actually be achieved through this repair? Is it even possible to make it safe and sound again?
Right, foundational.
Then, are there any alternatives to welding? Is there another way to fix this? And this one's vital. What actually caused the defect in the first place, and is it likely to happen again?
Ah, the root cause.
Exactly. We always recommend that quality control departments carry out an ongoing analysis of defect types. You need to discover the likely reason for them happening. Is it the material, the process, maybe even the welder's skill?
So it's not just about fixing the crack you see, but figuring out why it showed up to stop it recurring. Makes sense. What else is on that checklist?
You also need to figure out exactly how the defect will be removed. Which welding process are you going to use? Then, which non-destructive testing method, or NDT, do you need to confirm complete defect removal? You can't just guess.
NDT, right. Seeing inside without breaking it open.
Precisely. Then, will the welding procedures need approval? Or maybe reapproval? What's going to be the effect of that welding distortion and residual stress we talked about? Will heat treatment be required? What NDT is needed after the repair to demonstrate it's acceptable? And finally, will approval of the entire repair be required? And if so, how and by whom?
Wow, that's a comprehensive interrogation just to get started. It really sounds like repairs can range from, you know, fairly simple to incredibly complex, depending on the answers you get there.
Oh, absolutely. Repairs can be relatively straightforward, or they can become really quite complex, often needing involvement from various engineering disciplines, materials guys, structural engineers, welding engineers, to ensure a successful outcome. It's truly a team effort.
So, okay, let's say you've asked all those questions, you've got the green light. What does the actual process look like? Walk us through the general steps of a successful weld repair. What's the sequence?
Okay. In general terms, a welding repair involves a pretty detailed sequence of steps. You'd start with a detailed assessment, really pinpointing the exact extremity of the defect, often using those NDT methods we mentioned.
To find the edges.
Find the edges, precisely. Then thorough cleaning of the repair area is absolutely crucial. You've got to remove everything: paint, grease, rust, scale. Get it down to clean metal.
Okay.
Once that's done, the excavation site has to be clearly identified and marked out. No ambiguity.
And then you actually dig out the problem, right?
Exactly. An excavation procedure follows. This specifies the precise method, maybe grinding, maybe arc hair gouging, and any preheat requirements. Then, importantly, you use NDT again to locate the defect and confirm it's been completely removed.
Check your work.
Check your work. Absolutely.
Yeah.
You absolutely need an approved welding repair procedure or method statement. This specifies the process, the consumable, the technique, controlled heat input, interpass temperatures, all the critical parameters.
And the person actually doing the welding.
Only approved qualified welders should be used, no question. After the weld is complete, it gets dressed, which basically means it's cleaned up and finished properly, and then there's a final visual inspection.
More checks.
More checks. Another NDT procedure is carried out to confirm the repair was successful. Then you address any post-repair heat treatment requirements, followed by another final NDT after that heat treatment.
Wow.
And finally, any necessary protective treatments, like painting or coating, are applied. It's a rigorous sequence, almost like a surgical procedure, really, to ensure quality and safety.
Okay, let's zoom back in on those production repairs for a moment. This is about getting it right the first time, or, as you said, getting it right the second time, maybe, for our turbine blade at Apex Turbines.
Yeah.
How are these defects usually picked up and evaluated?
Right. Production repairs are typically identified during the initial production inspection stages. The evaluation of the inspection reports is handled by a welding inspector or perhaps an NDT operator. And it's really important to note that discontinuities, little imperfections in the welds, they're only actually classified as defects if they fall outside the limits permitted by whatever code or standard you're working to.
So a tiny ripple might be okay, but a crack is definitely not.
Exactly. A tiny, harmless ripple isn't necessarily a defect, but a crack that compromises the integrity. That absolutely is.
Got it. So how do they analyze what kind of defect they're dealing with in production?
Well, for instance, if you have an issue that breaks the surface, maybe right at the fusion face where the weld meets the original metal, it could be cracking. That might be related to the material itself, or maybe the welding procedure wasn't quite right. Or It could be something like lack of sidewall fusion, which often points more towards an issue with the welder's technique or skill.
Okay, and how do they check that? What tools?
To assess these, if the defect is open to the surface, you might use magnetic particle inspection, MPI, or perhaps dye penetrant inspection, DPI, to gauge the length of the defect. For its depth, how far it goes in, ultrasonic testing, or UT, is typically used. These are all non-invasive ways to essentially see inside the metal without damaging it further.
And when it comes to actually removing that defect during production, what are the specifics there? It sounds like it has to be a very precise job.
Oh, it is.
Yeah.
Extremely precise. If thermal methods like arc air gouging are used, which is like using an electric arc and compressed air to melt and blow away metal, a procedure qualification might be needed.
Why is that?
Because the intense heat generated can actually affect the metallurgical structure of the surrounding metal. It can risk cracking, either in the weld itself or the parent material. You might even need preheat just to prevent that cracking during the removal process.
Wow.
And it's also critical to maintain a specific geometry for the excavation. You need very precise, almost surgical kind of cut. We're talking about very exact depth to width ratios. That's crucial for the strength of the final repair weld and to avoid creating new stress points.
And cleaning.
In cleaning, yes. A critical step is grinding the repair area, typically just a few millimeters back to bright, shiny metal. This prevents carbon from the surface potentially getting impregnated into the weld metal or the parent material during the repair, which can cause problems.
That's fascinating how specific it gets down to the millimeter really emphasizes the precision needed. So once it's excavated properly and cleaned meticulously, what's next for these production repairs?
Well, NDT must confirm that the defect has been completely excavated, no traces left. And prior to rewelding, a detailed repair welding procedure or method statement has to be approved.
Right.
And then after the excavation has been filled with new weld metal, the whole weldment should undergo a complete retest using the original NDT techniques that found the problem in the first place.
To make sure nothing new cropped up.
Exactly. To ensure no new defects have been introduced by the repair welding process itself. You're essentially aiming to make it as if the defect never even existed. Erase it completely.
Okay, now let's shift gears. Let's talk about those in-service repairs. Back to our turbine blade that's already been spinning away in a power plant for years. These sound like a whole different level of challenge. Why are they considered so much more complex than production repairs?
They really are. In-service repairs are indeed far more complex, and for several layered reasons. First off, that turbine component, it's likely in a completely different welding position and condition than it was sitting nicely on the factory floor during production.
Right. Might be upside down sideways.
Exactly. And it might have been in contact with toxic or combustible fluids. That immediately necessitates a very strict permit-to-work system and extensive safety precautions before anyone can even think about starting work.
Makes sense.
The repair procedures themselves often look very different from the original production procedures because of these changes in environment and condition. The original procedure might just not be feasible anymore.
I can imagine heat would be a huge factor too, especially in a live or recently live environment, maybe with sensitive electronics nearby or something.
Absolutely. You have to consider the effect of heat on all the surrounding components. Things like electrical parts, seals, other materials that could easily be damaged by the heat of the repair procedure.
And heat treatment.
That's another major challenge. There's often real difficulty in carrying out any required pre- or post-welding heat treatments on a component that's already installed. And often, you have severely restricted access to the repair area itself. It might be buried deep inside some machinery.
Yeah.
And for really large fabrications, the repair might even have to take place on site without a shutdown of the whole plant or operation. That just adds huge layers of additional considerations and complexity.
Which brings us back to something you touched on earlier, the reason for failure.
Yes, absolutely critical.
Before you even think about picking up a welding torch in that complex in-service scenario, figuring out the reason for failure must be paramount, right? Especially given all those extra complexities. You're not just fixing a crack, you have to fix why the crack appeared in the first place.
Precisely. The reason for failure is absolutely vital for in-service repairs. You also need to know the specific material type and, ideally, the chemical composition for metals. If that cause-effect analysis isn't followed through really thoroughly, the repair is often unsafe. Sometimes, frankly, disastrously so. It's all about preventing a recurring, potentially catastrophic issue.
Okay. Let's dive a bit deeper now into some critical considerations that apply to pretty much any weld repair, whether it's happening in production or out in the field. First question, is welding always the best method of repair? It seems like the obvious go-to, but is it?
That's a great point. And no, not always. If a component has just a local irregularity, maybe a shallow defect, simply grinding out the defects and blending the area to a smooth contour might be perfectly acceptable,
When would that be preferable?
especially if the steel happens to have poor weldability, making welding risky, or if the part is under severe fatigue loading where a weld repair might actually make things worse long term. It's often better to slightly reduce the sort of theoretical factor of safety by removing a bit of material than risk introducing new defects, stress concentrations, and those tricky residual stresses into a potentially brittle material by welding.
Are there other non-welding options?
Sure. Other alternatives might include things like pinning, bolting, riveting, or even brazing, which is sometimes used particularly for cracks in cast iron.
So sometimes the best repair is no weld at all. That's kind of counterintuitive for a deep dive on weld repairs.
Yeah, but it's true. You have to consider all options.
What about comparing the current repair to previous ones? You mentioned policies, but are repairs ever truly identical? Should you just follow the last procedure?
That's risky. It's really critical to check if the repair you're facing now is truly like earlier ones, or if there are subtle but important differences. Maybe the section thickness is greater this time, or the steel is slightly different, maybe less weldable, or perhaps the restraint, how much the part is held in place and can't move during welding, is higher.
And those small changes matter.
They can have big implications. Even small changes can require a whole new approach. If there's any doubt, you absolutely need to go back through all those other critical questions we talked about. Essentially, treat it as a unique challenge every time. Don't assume.
And understanding the material itself, that seems incredibly important here. You can't just assume you know what it is, right?
You know, it's funny. Original drawings, especially older ones, might not provide nearly enough detail about the material's exact composition. Specification limits might have been less stringent decades ago when it was made.
So you need to test it.
A chemical analysis is often crucial, particularly looking for elements that really affect weldability, things like nickel, chromium, molybdenum, but also troublemakers like sulfur or phosphorus. For instance, sulfur-bearing free machining steel. It can cause significant hot cracking problems during welding. Big headaches.
And the cost of that test.
The small cost of that analysis, maybe a few $100s, maybe a bit more, can literally prevent a valuable component worth thousands or millions from being ruined. Or it could save you tens of thousands by showing that extensive preheat isn't needed. It's incredible how much the chemistry of a metal dictates whether a repair is even feasible, let alone how you do it.
That's a perfect example of how a tiny detail, the exact chemistry, can have huge financial and technical consequences. Okay, what about the strength required from the repair itself? Does stronger necessarily mean better when you're choosing the weld material?
Not necessarily, no. It's a bit counterintuitive again. The higher the yield strength of the repair weld, metal yield strength being, basically how much force a material can take before it permanently deforms, the greater the residual stress level is likely to be when the welding is done.
Back to those residual stresses.
Back to those, yes. So pushing that yield strength limit too high with a repair weld can actually introduce new weaknesses. It increases the risk of cracking and distortion later on. There's generally a practical upper limit for the yield strength of conventional steel weld metals, usually somewhere around 1,000 newtons per square millimeter. Going much beyond that gets tricky.
Right. We've talked about heat treatment a few times, preheat, post-weld heat treatment, PWHT. Can preheat always be tolerated, especially in these complex in-service environments? And what about that heat-affected zone, the HAZ you mentioned earlier? What are the concerns there?
Yeah, heat treatment is a big one. High levels of preheat can make conditions really difficult for welders, just physically hard to work around. And it can even damage the parent steel itself if it was originally tempered at low temperatures. Or it could harm nearby components like sensitive electrical wiring or seals.
Are there ways around needing high preheat?
Sometimes. Solutions to reduce the need for high preheat include using special ultra-low hydrogen consumables, welding rods or wires, designed to introduce very little hydrogen, which causes cracking, or using specialized non-ferritic weld metals, like austenitic stainless steels or nickel alloys, which behave differently.
And the HAZ, the area next to the weld.
Right, the heat-affected zone.
Yeah.
In very high-strength steels, you can actually get softening in the HAZ, although its extent can often be minimized with careful procedure control. Conversely, and perhaps more worryingly, You can get hard HAZs. Think of it like a super hard, brittle spot right next to the tougher weld in base metal.
Like a weak link.
Exactly. These hard HAZs are particularly vulnerable to problems like stress corrosion cracking, especially in environments containing hydrogen sulfide, H2S, like you find in oil and gas. In those cases, hardness below a certain limit, often 248 on the Vickers scale, is frequently demanded.
Even if it's too hard.
If you have excessively hard HAZs, they may require that post-weld heat treatment, PWHT, just to soften them up and make them safer.
So PWHT sounds generally desirable for dealing with hardness and stress, but is it always practicable or even necessary? It just sounds like another layer of complexity, especially out in the field.
It absolutely is another layer, and while it's often desirable, PWHT may simply not be possible for the same reasons high preheating might not be risk to adjacent components, access issues, cost, time.
Can you do it locally? Just heat the repaired area.
For large structures, local PWHT might seem like an option, but extreme care must be taken to follow the relevant codes very closely. Because if it's done improperly, local PWHT can easily introduce new residual stresses just outside the heated zone.
Oh, wow. Solving one problem by creating another.
Potentially, yes. PWHT is generally necessary for several key reasons. Maybe to improve toughness or enhance corrosion resistance, refine the microstructure of the metal, reduce that hardness we talked about, or relieve residual stress. You really need to understand why it might be needed in a specific case before you decide if you can risk avoiding it.
Okay. Given all these challenges, stress, hardness, distortion, what about things like fatigue and environmental resistance? Particularly if the repaired part is in a really critical location, like our turbine blade, where constant stress cycles are just part of the job.
That's a huge consideration. If the repair is in an area that's highly stressed by fatigue, meaning repeated loading and unloading, especially if it's repairing a crack that started due to fatigue, then you have to expect inferior fatigue life compared to the original part. Unless the weld surface is ground exceptionally smooth, perfectly blended, and absolutely no surface defects are left behind, any little notch can become a starting point for a new fatigue crack. And certain types of welds, like fillet welds where you can't easily access and grind the root smooth, are simply not acceptable in high fatigue stress areas. Full stop.
And the environment it operates in.
Beyond just mechanical fatigue, you absolutely must consider the environment. Is corrosion an issue? Stress corrosion cracking. Corrosion fatigue, the combined effect. Thermal fatigue from temperature cycles. Oxidation at high temperatures. The filler metal used for the repair should, as a minimum, be at least as noble or resistant to that environment as the parent metal it's joining.
And PWHT comes back into play here too.
It can, yes. For preventing stress corrosion cracking, for example, PWHT may be necessary specifically to restore the correct metallurgical microstructure, reduce that dangerous hardness, and alleviate the residual stress that drives the cracking.
Okay, and inspectability. After all this complex work, making sure the repair actually worked and is sound, are there challenges there too? Can you always check it properly?
Yes, inspectability itself can be a challenge.
Yeah.
For demanding service conditions, you often want to use radiography, like X-rays or ultrasonic examination, sound waves, to check the internal quality. But problems can arise if, for instance, stainless steel or nickel alloy filler metal was used for the repair.
Why is that?
Those materials can sometimes make interpretation of radiography or UT results difficult. They have different properties that can interfere with the tests. And magnetic particle inspection, MPI, which is great for surface cracks on ferritic steels, is not suitable for non-magnetic materials like stainless steel.
So what do you do?
It means it's even more crucial to carry out the procedural qualification test very, very critical beforehand. And it emphasizes the need for highly motivated, well-supervised, skilled welders during the actual repair to minimize the chance of defects occurring that might be difficult to find later. You rely more on process control.
Right. Lastly, what about as-welded repairs? That means doing the repair without any post-weld heat treatment, right? It sounds like you're skipping a potentially important step, but is it common?
It is quite common, actually. Repair without PWHT is pretty normal in situations where the original weld wasn't heat treated either. If the original design didn't require it, often the repair doesn't, assuming conditions haven't changed drastically.
But not always.
Not always. However, some alloy steels and many thick-section components, just due to their sheer size and the stresses involved, do fundamentally require PWHT to maintain reasonable toughness and sometimes corrosion resistance. But here's the kicker we keep coming back to. Actually, performing PWHT on components that are already in service is often not easy, or sometimes even possible.
Yeah.
And as we said, attempting local PWHT can sometimes cause more problems than it solves, except perhaps in very simple structures. It's always a balancing act, risk versus reward.
And speaking of balancing acts, let's finally talk about the cost. Because I think this number might genuinely surprise you, our listener, as it certainly did me when I first saw it. The cost of the actual weld metal deposited during a weld joint repair can be up to get this 10 times the cost of depositing the same amount of weld metal during the original fabrication.
10 times. Yeah, it's a stark figure, isn't it?
10 times. That's truly astonishing. I never would have guessed it was anywhere near that high. Why? What makes it so much more expensive?
The financial impact is profound, and it goes far, far beyond just the cost of the welder's time or the welding consumables, the rods or wire.
So what else is included?
Think about it. It includes the inspector reports identifying the defect, the detailed, careful defect removal process, multiple stages of that non-destructive testing before, during, after, extra documentation, procedure qualifications, method statements, possibly engineers' time for analysis, and potentially huge penalties for equipment downtime and lost production while the repair is happening.
Ah, okay. All those extra steps add up.
Yeah.
Fast.
Every single one of those steps adds significant cost. It really is a testament to the old saying that prevention is truly, truly cheaper than cure, especially in welding. Getting it right the first time saves an enormous amount down the line.
So we've taken quite a deep dive today into this incredibly intricate balance. Financial, structural, metallurgical, procedural considerations, all involved in weld repairs. From that hypothetical shop floor at Apex Turbines making new blades, to a blade that's been working hard out in a power plant for years, we've really seen the critical distinction between production and in-service repairs and their unique, often layered challenges.
What's truly fascinating, I think, is how something that might seem like a simple fix on the surface is actually this highly engineered, multidisciplinary solution. It requires incredibly careful thought, planning, and execution at every single step. This whole process is really a testament to the depth of knowledge required in engineering and infrastructure, just ensuring the safety and reliability of everything from bridges and pipelines to power plants and aircraft.
It really is. And hopefully for you, our listener, understanding this process is maybe a bit of a shortcut to being well-informed about a critical aspect of how our modern world is built, maintained, and kept running safely.
Yeah.
It definitely makes you look at a repaired bridge or a working factory machine, maybe even your own car, in a whole new light, doesn't it?
Absolutely.
So here's a final thought to leave you with. Given these hidden complexities, the surprising costs, and the absolutely critical safety implications we've talked about with weld repairs, what other seemingly simple fixes or processes in other areas of our lives might actually hide similar layers of complex engineering, detailed decision-making, and hidden trade-offs that we just never consider? We encourage you to keep looking for those deeper dives in your own world.